Bismillahirrahmanirrahim. Assalamu alaikum warahmatullahi wabarakatuh. My name is Oladimeji Tihe, the Ss2 Physics teacher of CTY Model College, Ibadan, Oyo State, Nigeria. Hello students, you are welcome to the period 3, the last for the week 7 of our e-learning physics class for third term 2019-2020 academic session. And the topic of discussion for this period is going to be critical angle and total internal reflection of light. Remember, the topic we've been studying is the refraction of light waves. And so far so good, we are able to consider refraction of light through rectangular glass block, refraction of light through triangular glass prism. We also look at some effects of refraction. Where you are given the various formulae for finding refractive index. Refractive index in terms of velocity, that is velocity of light in here over velocity of light in the medium. Refractive index in terms of angle of incidence and angle of refraction. That is, refractive index is equal to the ratio of sine of angle of incidence to the sine of angle of refraction. We also look at refractive index in terms of wavelength, which is given as the wavelength of light in here over the wavelength of light in the medium. We also define refractive index in terms of apparent and real depth, where the refractive index is given as the real depth over apparent depth. We also talk about apparent displacement, which is the difference between the real depth and apparent depth. We also give refractive index in terms of angle of minimum deviation and refracting angle of triangular glass prism, where the refractive index is given as the sine of half of angle of the m plus a over sine of half angle a. Now, today we want to look at critical angle and total internal reflection. To have a clear understanding of this topic, first of all, let's go to the diagram below and analyze what we see on the diagram. Yes, the figure ABC, they represent a light ray traveling from glass to here. So first, let's consider figure A. Figure A shows a light ray, which is represented by the line XY, that is traveling from glass to here, that is from a denser medium to a less dense medium at an angle of incidence I. From the figure, two things can be observed. Both refraction and reflection take place at the same time. YS represents the refracted ray, while YR represents the reflected ray. But the refracted ray is stronger than the reflected ray. That is, there will be a strong refraction, while there will be a weak reflection. So the incident ray makes with the normal is the angle of incidence high, while the angle the refracted ray makes with the normal is the angle of refraction. So now if we increase the angle of incidence gradually, we discover that the angle of refraction will also increase gradually. So until we will get to a particular angle of incidence, which is the same as the critical angle of the glass, where the angle of refraction will now be 90 degrees. So the refracted ray will now pass through the edge of the semicircular glass block as shown in figure B. In figure B now, the angle of incidence with the normal is now equal to C, the critical angle of the glass. Then the angle of refraction in the less dense medium will now be 90 degrees. That is, the incident ray passes through the edge of the semicircular glass block. Still, there will be a strong refracted ray and a weak reflected ray. So, therefore, critical angle can be defined as the angle of incidence in the denser medium, that is the glass, when the angle of refraction in the less dense medium, that is the air, is equal to 90 degrees as shown in the diagram. If we continue to increase the angle of incidence I, shows that I now is greater than the critical angle as shown in figure C. We will observe that there won't be any refracted ray again, that is no more refraction. Instead, all the ray, incident ray, will be totally reflected as shown in figure C. Then we have a strong reflected ray and no refraction. And when this occurs, we say there is total internal reflection. Therefore, total internal reflection is the complete reflection of light ray in the denser medium when the angle of incidence is greater than the critical angle of the glass, shows that there is no refraction and there is total reflection. So now let's run through what is written. When light travels from an optically denser medium, e.g. glass, to an optically less dense medium, e.g. air, refraction occurs with faint or weak internally reflected ray in the denser medium as shown in figure A. As the angle of incidence increases, the strong refracted ray bends towards the glass to air interface. For a particular angle of incidence, the refracted ray lies on the air to glass interface as in figure B, and the angle of incidence for which this happens is called the critical angle. We therefore define the critical angle as the angle of incidence in the denser medium for which the angle of refraction is 90 degrees when light travels from an optically denser medium to an optically less dense medium. If this angle is increased, the ray will be reflected internally in the denser medium, shows that there is no refraction as in figure C. This is what is called total internal reflection as explained earlier. Therefore, for total internal reflection to occur, two conditions must be satisfied. One, light must travel from an optically denser medium to an optically less dense medium. If otherwise, total internal reflection cannot take place. That is, if the light is traveling from an optically dense to an optically denser, there won't be any total internal reflection. For total internal reflection to occur, the first condition is that light ray must be traveling from optically denser medium to an optically less dense medium, e.g. from glass to air, from glass to water, from water to air, etc. But if light ray travel from air to glass, total internal reflection cannot occur. If light rays travel from air to water, total internal reflection cannot occur, and so on. Condition 2, the angle of incidence in the denser medium must be greater than the critical angle. You can see that's what happened in figure C. When we now increase the angle of incidence beyond the critical angle, that is when our angle of incidence is greater than the critical angle, that's when we have total internal reflection. So the angle of incidence must be greater than the critical angle. So the two conditions again are light must be traveling from an optically denser medium to an optically less dense medium. 2. The angle of incidence in the denser medium must be greater than the critical angle. In other words, the critical angle of the denser medium must be exceeded. Critical angle and refractive index. So this will show us the relationship between the critical angle and the refractive index. In terms of refractive index, in terms of the critical angle, total internal refractive index is given by n is equal to 1 over c, where n is the refractive index and c is the critical angle. So the reciprocal of the sine of angle of critical is equal to the refractive index of the medium. So let's run through this example. This is the 6th example as far as this topic is concerned. The refractive index of glass is 1.5. What is the critical angle for the glass to air boundary? Solution. Refractive index is 1.5. Critical angle is C. So applying the formula, n is equal to 1 over c. 1.5 is equal to 1 over c, making sin c the subject of the formula. That's 1 over n, that is 1 over 1.5. Then making c the subject of the formula from here, we have arc sine of 0.6667. And this will give us 41.8 degree. Approximately this is 42 degree, which is the critical angle of the glass. Applications of total internal reflection. So total internal reflection is found applicable in the following. 1. Prism periscope, mirage, optical fibers, fish field. Let's look at prism periscope. This instrument is produced by arranging two isosceles right angle triangular prism as shown in the figure below. Light from the object is turned by the top prism through 90 degree and emerges from the side BC of the top prism. The bottom prism turns the light again through 90 degree and the observer sees an image of the object at the position I. As you can see, so this is similar to the mirror periscope, but the only advantage of this over mirror periscope are the following. 1. Prism periscope produces only one image, but plain mirror periscope produces multiple images due to multiple reflections. 2. Prism periscope reflects more light than the plain mirror periscope. Therefore, the image appears brighter than the one produced by plain mirror periscope. 3. Prism periscope is not coated at the back like the plain mirror periscope, so its back cannot be damaged. So, this is where we are going to end the topic under reflection of light waves. Please, the students are advised to go over the topics, read in between the lines, and understand everything stated in the topic. The questions on the topic will be uploaded on the school portal. The students should log on to the school portal, look for the questions, and provide solutions to them. And they should upload their solutions back at the appropriate place on the school portal for marking. And they should do so on or before the deadline that will be stipulated on the question. Until next week when I will come your way again, my name is Oladimeji T.A., your physics teacher, saying Salamu alaikum wa rahmatullahi wa barakatuh.